In this chapter, we shall be seeing about buffer overflow. Now, buffer overflow attacks are the mainstay of finding out vulnerabilities in system services and software, and hence should be understood well in order to create exploit code in the process of exploiting the detected vulnerabilities. Before going on to the topic, it is important that we make ourselves acquainted with several terms which shall arise during the course of this module, such as exploits, payload or shellcode, vulnerability, and 0 days. Vulnerability is defined as the weaknesses present in a device which would lead to its exploitation. Exploits are sets of code or program which are used to trigger specific vulnerabilities in a system. Payload is the data which is to be sent to the victim computer along with the exploit, with the purpose of getting a command line interface from the target to the attacker. Whereas 0 days are undisclosed or recently released vulnerabilities for which no current patching mechanisms are present. Storage is an essential aspect of any computing device. When it comes to efficiency of a CPU's computing, it is important that it has access to storage spaces which are comparable to it in speed. In a device, this purpose is served by registers. Registers are among the fastest memory spaces present in a computer. Some of the commonly used registers are EIP, the extended instruction pointer, indicates the address of the next instruction which is to be executed by the processor. This gets saved onto the stack for later use. Next is ESP, which is the extended stack pointer, which indicates the top of the stack, which is used for reference when it comes to push and pop operations during program execution. The next would be EBP or the extended base pointer, which serves as a static pointer for referencing the information on the stack like variable and data using offsets. Its value remains same throughout the program. In buffer overflow, memory visualization is important to help understand the storage mechanisms in a better way. For that purpose, knowledge of a few data structures is a good start. Here, we shall focus on two commonly used data structures called stacks and heaps. Stack is a last in first out based data structure that is used by programs for passing arguments to relevant functions as well as referencing local variables. Stack serves the purpose of temporarily storing the variables utilized in a function and are created and destroyed according to the invoking and stopping of the function. Heap is a data structure that is used by a program to store data which is created dynamically during runtime operations. Like stacks, it is used for temporary data storage and is required only for the invoking of malloc function which allocates memory to dynamic variables. Buffer overflows, as I mentioned earlier, are essential to finding out vulnerabilities in system and software components. This condition, as the name suggests, occurs when a program exceeds its allocated memory space due to some reasons and spills the extra data onto the adjacent buffer, thereby overwriting the existing values. Such conditions are usually brought upon by specifically created user inputs into the program, leading to an application displaying erratic or abnormal behavior, thereby allowing an attacker to drop crafted code on the system and compromising the security measures. If in any case any attacker finds this kind of vulnerability in widely used software, then they use it maliciously to gain access to machines. Since the concept of buffer overflow is dependent on inadequate checks on memory space, so the dependence of such an attack is on two criteria, such as lack of proper boundary testing and execution of code residing on a stack by a machine. The first criteria is fairly common, with applications and mostly returns a segmentation fault or bus error. For exploiting buffer overflow vulnerability, it is important that the attacker crafts the data in order to direct program execution to malicious code rather than just putting in random input, which will only generate errors but will have no negative impact in terms of security. In this slide, we shall discuss about stack-based buffer overflows. A stack-based buffer overflow occurs when a program input pushes current data from the stack, thereby leading to malicious code execution and thereby a security breach. The data from the stack is replaced by specifically crafted values by the attacker, which enables it to redirect the program execution process to the malicious code, which in most cases is shellcode, which spawns a terminal interface which allows the attacker to execute remote commands to the target device. Such attacks are fairly common in system services. Apart from stack overflows, another common type of condition called heap-based buffer overflow is prevalent in exploit testing. As we have seen earlier, heap is used to dynamically allocate memory to program variables during runtime, mainly through the malloc function. In a heap-based buffer overflow attack, an attacker overflows a buffer which is placed on the lower part of heap, overwriting other dynamic variables which cause unexpected and unwanted effects. Just like in a stack-based buffer overflow, in most environments, this may allow the attacker to control over the program execution. Now, from an information security perspective, understanding these conditions would be futile if some countering mechanisms are not evaluated and employed. Some of the commonly used countermeasures for buffer overflow attacks are as such, like choice of better languages such as Java or .NET, using library security, executable space protection, address space layout randomization, deep packet inspection, and disinfection parameter. Now that the concept of buffer overflow is covered, let us move on to another section of this module termed as exploit writing. Exploit is a set of code or program which is used to trigger specific vulnerabilities in a system. It is the mainstay of a targeted attack on a system via proper vulnerability assessment. Along with the exploit code, a payload is attached which defines the nature of the data to be executed, which in most cases is shellcode. The main purpose is to get access of the system and control the system. However, it is not necessary that every vulnerability will result in the target being compromised. It may result from anything between denial of service, namely making the application crash, to code execution. Since this is a highly specialized domain, there are some prerequisites for someone who wants to pursue this as a career. Some of the prerequisites have been listed as shown, like good knowledge of programming, preferably in C, C++, Python, and familiarity with memory addressing concepts, assembly language mnemonics, assembly language opcodes, data structures, specifically stack and heap, buffers, references and pointers, registers, and good knowledge of program execution flow. Now, based on the type of environment, it is important that exploits be classified into different types. That helps the penetration tester to accommodate several variables in a penetration test, which helps him to conduct a thorough penetration test. Exploits are generally categorized using the following criteria, such as the type of flaw that is taken advantage of, such as BOF or dangling pointer, remote or local. Remote exploits refer to vulnerabilities which can be exploited from a network remotely, while local exploits need to be executed on the same machine. RCE are more important and critical than local exploits since user interaction is almost removed. The result of the exploit. Some of the examples being denial of service and remote command execution. Stack-based exploit is dependent on a stack-based buffer overflow, which occurs when data more than the stack space has been filled out. The data from the stack is replaced by specifically crafted values by the attacker, which enables it to redirect the program execution process to the malicious code, which in most cases is shellcode, which spawns a terminal interface which allows the attacker to execute remote commands to the target device. The data stored in a heap is through functions which dynamically allocate memory, such as malloc. As we know by now, heap is first in first out and it grows towards the higher memory address in the memory. When an attacker enters the data in heap, it overflows the adjacent data that is in the lower part of the heap. If any application takes an input from the user and copies it in the memory without checking it, a heap overflow may occur. And most of the times, it can also result in arbitrary code execution due to data entered by the attacker, resulting in compromising the application and the system. Some other types of exploits include format string and integer bug exploits, which are widely used to test applications. Format string exploits are used to crash software or to execute malicious code through string type crafted input. This attack is possible because the user input is filtered as a format string parameter in several C functions that perform formatting, such as printf. A malicious user may use the %s and %x format tokens, among others, to print data from the stack or possibly other locations in memory. Integer bugs are exploited by passing an oversized integer to integer variable. It may cause overwriting of valid program control data, resulting in execution of malicious codes. Integer bugs are very often found and exploited in applications to achieve various purposes. Continuing with the classification of exploits, here we shall see about remote and local exploits. Remote exploits are those exploits which can be executed on the remote system. For example, a FTP server taking a malicious input from a client machine, resulting into a buffer overflow which gives access to whole server. Remote exploits tend to exploit the services running on the system to gain access to the systems. They are generally non-root and not system services. Remote exploits are carried out over a network. Local exploits are those exploits which can only be executed on the local machine, where the vulnerability has been found and cannot be mutated to a remote exploit. Local exploits usually exist in the applications that are locally installed on the system and results in privileges escalation. In this slide, we shall discuss the process of writing an exploit. For the sake of clarity, I will list the steps in a sequential manner. The steps are as follows. Identify and analyze application for any vulnerability. Next, attach it with a debugger and check whether the return value can be overwritten by providing input to the vulnerable application. Next, in case of success, automate the process using a scripting language, preferably Perl or Python, to make the work easier. And the final step would be to check the dynamic link libraries loaded onto the RAM and try to find an address where shellcode can be injected to redirect the program execution flow to the desired place. This, by no means, is a detailed process, and the steps may have several divisions, but the overall process can be summed up as such. Now, shellcodes are an integral part of the testing process and are extremely essential to constitute proof of concepts of vulnerabilities. Shellcodes are a set of instructions which use system calls and are used by exploits for carrying out some actions on client machines. They are executed after a vulnerability is exploited, and they are working machine instructions in a character array within an exploit source code. They are operating system dependent, as we have different system calls in different operating systems. Even in Windows itself, different service packs are involved in different system calls. Shellcodes are machine instructions which are used to directly process via the desired instruction at memory location. As we are nearing the end of this module, the final discussion will be about the construction of shellcode. Once again, for the sake of clarity, I shall attempt to list out the process in a sequential manner. The steps of writing a shellcode are as follows. Write the code in assembly language or in C language and disassemble it using GDB or OLEDBG. Get the argument and system call IDs for the operating system you are targeting the shellcode for. Convert the assembly codes into opcodes and eliminate null bytes from it. Next would be to compile it and execute. Finally, inject the running code into the previous working exploit to check if it is working or not. So this concludes the chapter on buffer overflow and exploit writing. Up next is a demonstration to illustrate the concept explained here. Thank you.
Hi, today I'm going to show you how to do buffer overflow attack and what is buffer overflow attack is all about. In this video I'm going to show you a demonstration of a simple program which is written in C language and how to trigger a buffer overflow attack in it. So let's first understand what buffer overflow attack is all about. So buffer mean it is a block of memory actually. So like buffer overflow attack is occur when too much of data is entered into the buffer, then it can handle so this may lead to a executing an arbitrary code if a certain memory pointer is written. It means if a buffer if you like wanted to trigger a buffer overflow attack, so for a specific memory for a specific process there is a buffer assigned to that process, a buffer of memory, and if we try to put as much as data into that buffer which is actually not meant for it, then it will trigger a buffer overflow attack. The process will not able to handle that much of data and it will trigger it and it will actually overflow the memory. So this is all about buffer overflow. So let's see a practical demonstration of how to trigger a buffer overflow attack in an application or a program. So let's open an editor. I'm using here Nano and write with a program. My name is overflow.c. So I just zoom in so that you can give a good picture of it. Okay, so yeah, so let's write a simple C language code. For those of you who are not familiar with the programming language, you don't need to worry. I just keep on explaining you what are the different functions I am right now using in it, so that you feel much more comfortable. So let's type in a small program. This is a simple header file which is used in C library. It's used for standard input and output, for taking an input and showing an output on the console. Void main. This is a main function where the execution take place, or where the main execution start. And here we write our code. So I'm going to define a character pointer with the name variable. I'm going to define another character name variable actually pointers with the name command. Let's assign this character, this pointer name let's assign this character pointer name to some blocks of memory by using a function called malloc. This function will dynamically assign memory at the runtime to this pointer. Okay, So I have just assigned 10 bytes of memory to my name pointer, and I'm just going to assign 128 bytes of okay, so I have just assigned a 10 bytes of memory to the name pointer, and I'm just going to assign okay, so I'm just assigned a 10 bytes of memory to the name pointer, and I'm going to assign 128 byte of memory to the command pointer. So let's assign, and I used a function, that is a malloc, which is available in C library for assigning memory dynamically at the runtime. So till now, so I have just used created two pointer by the name of name and command, and I just assign a memory to those pointers by the name of by using the function called malloc. So let's print their memory addresses onto the console. So here I'm going to use a function called printf, which is used to print anything onto the console. Okay, so %d is used to show output of any integer onto the console, and /n, which is \n, is used to for the next line in C language, or any C or C++, you can say. Okay, so this big line basically shows the memory address of name variable onto the console, and here I'm going to use the same method for showing the output of the command variable onto the console. And as I told you, %d is for like showing the integer variable output on the screen or console. Okay, yeah, so let's print the difference of these two memory addresses onto the screen. So we'll see like whether difference is maintained, like so we'll see whether the difference is maintained, like if we keep on changing our program, or the differences between the name memory allocation, the name variable memory location, and the command variable memory location, is it keep on changing, or the differences remains the same. So let's see. So address, or I say difference between addresses, fine, yeah, that's nice. And that is when I use the %d, and with \, and with the next line, as I told you, and yes, command minus name. That's good, beautiful. Okay, so now okay, so what we have done so far, we just used printf function for 3 times. The first time we'll just use to display the name memory location of the name variable. The second time we used to display the memory location of the command variable, and the third time we have used the differences between their memory addresses on the console of the screen. So let's type in again the printf function and just display a message on the console. Just enter your name for like asking name of the user or the one who is going to use this program. Okay, so just this simple message which is going to show onto the console, like when the user run this program, it say, okay, please enter your name or enter your name. So let's say, and I'm using here variable function called gets take the name from the user from the console, and that is a function which is inbuilt in C library. And with again the printf function, I'm going to display the name entered by the user onto the screen. I have again used that the same function, that is printf, and now I'm giving hello, just a message, a good message onto the screen, and type in %s, type in %ds. Why I'm used this why I've used %s? It's simple to, if I wanted to show onto the console, if and the thing that I'm going to show is it's a string, or another case, we just see that if I wanted to show onto the screen, if the outcome is in the form of integer, then I'm going to use %d, and if the outcome is in the form of string, so I'm going to use %s. Now again \n for the next line, and single quote, comma, and name. Yeah, and my last command is to use system function, which is predefined and inbuilt into the C library, and that is, and giving this system function command variable as an input here. So we have just completed our program. So we're just going to give a quick run of it. So what we have done, we have just used a standard library, that is #include stdio.h. Then we have defined our function, that is void main, and then in the main function, which is going to execute, we have just defined two variables, that is, we just defined two character pointers, that is name and command. After that, we have just assign some bytes of memory to both the pointers, that is, I have just assigned name variable a 10 bytes of memory with the help of using a function called malloc. Then in command variable, I have just assigned 128 bytes of memory to the command variable with the help of function called malloc. Then in next line, I have just printed the memory address of the name pointer, and next line I have just showed on the console the memory address of the command pointer, that is command variable, that's command character pointer actually. Then in the next line, again I have just show the difference between the command pointer and the name pointer memory addresses. Then I have just asked for the name from the user with the help of the gets function, which is pre-built in C library. I've just used the gets function, and once the user enters his name, it shows onto the console. And in the end, I have just defined another function, that is system, and giving him as an output, that is command. So this function is something which is going to trigger a buffer overflow, and how this function is going to trigger a buffer overflow, that is quite a little bit tricky. So we'll just first of all save this program by using Control O, that is a key for a nano editor, and Control Z to coming out of this program. Now I am onto my console. So let's just compile this program with GCC, that is GCC space name of your program, that is overflow.c, and -o for output, and the final name of your program, that is the compiled version of your program, that is overflow, and hit enter. You'll see many errors onto the screen, so just don't worry about it. Okay, fine. So let's compile this program now. Just press Ctrl O to write all the things, and just Ctrl Z to coming out on the console, and let's compile it. GCC overflow.c -o for the output, and the name of the program that you wanted to write. So you can use any name, whatever you like to have. So I'm using here overflow. Just type it. Okay, so you'll find so you will find a little warning which you do not need to bother about from the system itself. So we'll just compile our program now, and now we just run it. So just type in // name of your program, that is overflow. Yeah, beautiful. So now it's running. It shows the address name of address name is for the variable, that is a that is name is 144510984, and the command is address of the command is that is my command character pointer is 144511100. So, and the difference between is 16 bytes. So if I'll again run this program, will the difference remain the same or not? So let's give it a shot now. But now for the time, this program is asking for a name from the user. So I just type in Inobus. Okay, and hit enter. Yeah, it says hello Inobus. Again, run this program. We'll see. Yeah, so once I'll again run this program, I can see that the memory addresses got changed, but the differences remain the same. So this means as the malloc is functioning in a proper manner, and it's keep on assigning different memory addresses at the runtime to my different to my those two variables, that is name and command, but the differences between their differences is remain the same, that is 16 byte. So as I told you, malloc is a function which is predefined function in my C library, which assign bytes of memory to my variable at runtime, fine, dynamically actually. So now my purpose is to trigger a buffer overflow attack into this program. So let's suppose as I have assigned name variable 10 bytes of memory, and I have assigned command variable 128 bytes of memory. So let's see, suppose if I exceed that level of memory, or the level of bytes, so what will happen? So I just type in before in my program Inobus. So let's exceed this characters. I just type in Inobus knowledge solutions now and hit enter. Now the interesting part you can see onto your screen, that at this point of time, if I have used in my previous output, I have just used these much of character, that is 1 2 3 4 5 6 7 8, only 8 alphabetic characters, and the program is running quite well. But if I've used maybe I've just exceeded my characters, and I've seen a error on the console that says e solutions not found. It may say it's not recognize any sort of command, something like that. So if I type in like e solutions onto my console, so what will it say? Yeah, it says bash e solution command not found. So this is something really interesting. So how about this, if I trick this program to trigger a buffer overflow? Let's suppose I'm running my program again, fine, and now what I'm going to type here is Inobus knowledge, but now what I'm going to type is a command which is there already present in a system. So let's suppose I'm going to type this command, cat space forward slash etc forward slash password. Boom, you can see onto your consoles what we are able to do. We are just able to see the password directory file in Linux. That's amazing, isn't it? So we'll just possibly able to trigger the buffer overflow attack in my simple program. So what I have just done is I have just replaced those characters with the system command, and as I've told you in my program, in the end of line, I have just defined a system function, and what actually this function will just jump out of the memory and executed the command which is not really mean to execute. So it's actually a problem with this program. It's actually a problem with the gets function, because it's not bind their a character which is taken from the user input. So out of the bound, it's something like that, you just given him some input and he just not able to handle it, and it got jumped into some other memory location. So this is what buffer overflow is all about. Like you have just defined a buffer to a program, but the buffer will not able to handle as much as input. Like suppose I have just assigned 10 bytes of memory to the buffer, but I have supplied 20 bytes or maybe more than that, 50 bytes of characters or the input to that specific buffer. The buffer will not able to handle it, and it trigger onto the some other location, or just trigger my program. So buffer overflow will able to execute any arbitrary code onto the console, any arbitrary code onto the remote console. So this is what buffer overflow is all about. And in the simple program, it's just quite simple. For those who are not aware of C programming language, I've just explained each and everything what actually the functions I have just used so far. So in this program, I have just demonstrated how a simple buffer overflow can cause a big problem to your machine. This is really simple. There are more complicated buffer overflow attacks than this, but this is really interesting. So yeah, this is all about buffer overflow. Thank you.